So, recall last week we had discussed the Bloch's theorem and how the periodic potential leads to energy bands and energy gaps at Brillouin zone boundaries. And finally, what we discussed was applying periodic boundary conditions to Bloch wave functions, and we got that when the periodic boundary condition is applied over a length L, periodic boundary condition is applied over a length L, which is n times A, n is the number of cells. In that case, you get K L equals 2 pi n, where n equals 0, plus minus 1 and so on, and K equals 2 pi over A n over n. And there are exactly n K states in one band. This is where we stopped last week, and what it meant was that if I have an energy band K E K, I will just make two of them up to the Brillouin zone, K extends from minus pi by A to A, and here is the first band, here is the second band. Then the total number of states in this, total number of K values, is K is quasi continuous because n is integer. So, all these number of K values that are there independent states are going to be n in number in this band as well as in the upper band. Exactly same K values will exist here also. So, I am just indicating these are the quasi continuous K values, and I have E versus K. I have shown some points, and taking into account electron spin, which can take two values, we have 2n electrons that occupy the full band. So, when the band is full, it will accommodate 2n electrons. All the states in the Brillouin zone are occupied, including the electron spin, when the band is full, and this has implications. Now, let us take it case by case, and I want to remind you again that I am dealing with one dimensional cases. When we go to 2 or 3 dimensions, there will be a little more subtlety involved, but general conclusions that we arrive at right now are going to be valid with little changes, and I will give you examples of that. So, let us take them case by case. Suppose A, we have atoms with one free electron each. In that case, total number of electrons that are free to move in the crystal, free to move in the crystal is going to be n. And therefore, if I look at the band, it is going to be only half filled. So, it has all the states up to certain energy E that are filled. So, all these are filled and these are upper states are all empty. In that case, if I give even small energy to an electron here, let us say this red one, if I give even small energy by any means, it can gain energy and go to the next level. It can gain energy and go to the next level. It can gain energy from here and go to the next level. So, I can excite these electrons. If I do that by applying an electric field, and let us see what happens. So, I have this band and suppose I apply an electric field in this direction. In that case, in the very first qualitative approximation, what I can say is that the potential energy for electrons in this direction on the left hand side in the direction opposite to the electric field would be lower, and because they will tend to move that way, and on the right side it will be higher. So, I can think of this band as if it has tilted a bit. Where this there is a finite difference in the energy on the right hand side and the left hand side. So, what could happen is electrons out here in the filled band would gain energy and come to the other side. So, they will start occupying these empty states, and they start occupying these empty states, they are moving because they are going to a different k state, right. And velocity, I will talk about it later. We have, you can guess the velocity of electron will be given by the group velocity, which is dE by dk. So, let us start gaining velocity. Once they reach on the left hand side, they start moving from here. So, when they start moving, that means there will be a current. So, if bands are not completely filled, applying an electric field will lead to a current. If it leads to a current, that means these are metallic systems, half filled bands imply systems. Once that I have explained this, just a word of caution. The word of caution is, I have very qualitatively, when I made this picture up here, let me encircle this with the green color thing. When I made this picture here, I tilted the band. It is a very qualitative picture, because remember this band has been plotted in k space, which is not the same as the regular x space. So, when I said it is tilted, it has to be taken with a little very qualitatively. What is actually happening is the electron is gaining energy and it is going to a higher energy state. It can move to a higher energy state. So, that there is a disbalance between the electrons which are filled on one side, and on the other side there is a velocity disbalance, and that leads to the current. So, bottom line is that when you have these half filled bands, electrons can gain energy from the applied electric field and lead to a current. So, half filled bands are going to be metallic. So, conclusion number 1. Half filled bands give metals. Along the same line, I can say that if bands are not fully occupied, this implies metals. Now, let us see what happens if an atom per cell, suppose there is only one atom per cell, has 2 free electrons that can go into the band. In that case, let me make this picture again, the band diagram. I have minus pi by a to pi by a, and this whole band is filled with electrons. It has occupied all the states. And the next band has a gap. So, if I apply a weak electric field, so let us apply an electric field. It would require for electron to gain minimum this energy equal to the gap, let us call it delta E gap, so that it can go to the next band. If it does not require that much energy, it cannot move to the next band. On the other hand, if it remains in the same band, it has nowhere else to go. A little like when you take atomic states, unless you apply some minimum energy, the electron does not go to the higher level. So, it does not accept that energy. Similarly, here if I apply a weak field, the electron would not accept any energy from it, it will not move. And if the electron does not move, that means there can be no current. So, conclusion 2. If a band is fully filled, then an applied electric field does not give any current, and this implies the system is an insulator. So, these are the two pictures that are emerging from the band theory, that if I have a fully filled band, there will be an insulator, the system would be insulating, and if I have a partially filled band, then the system will be metallic. So, let me make this partially filled band here and fully filled band here. This is an insulator, and on the left hand side I have a metal. So, you can also say that if I have in a crystal one atom per unit cell and each atom gives only one electron, I will have a metal. If each atom gives 2 electrons, I will have an insulator, and there is something in between, and that is known as a semiconductor. There will be a whole lot of lectures on semiconductors, but right now let us just introduce the idea, and the idea is that again I have band which is fully filled, however, the next band has this gap, delta E gap, which is very small. If it is small, there could be these electrons going up due to thermal energy. They will obviously reside at the bottom of the band, and they will go from here. So, some part here will become empty. And this is due to thermal excitation. Remember, thermal excitation kBT at room temperature is of the order of 25 MeV. So, this band gap has to be very small, so that these electrons are excited to the upper band, and in that case I have these electrons which can move in an empty band, and there will be some conduction. That conduction would be temperature dependent. So, these are semiconductors which are essentially insulating, but due to delta E gap being small have electrons in upper band, and therefore, that leads to conduction. You can easily see that the conductivity of these systems, conductivity is going to be highly temperature dependent. So, this is the band theory explanation of the materials, metals, insulators and semiconductors. So, let us conclude again. 1. Metals. 1 free electron per unit, and the band is half filled. Examples for this will be sodium and all the alkali earth in that. Then in that case, magnesium will not be a metal because it has 2 electrons, free electrons. Mg is, remember, 3s2. It will not be a metal, however, it is. So, I will talk about that in a minute. And number 2, this is general observation, insulators, 2 free electrons per unit, and the band fully filled. And third category is semiconductors, essentially these are insulators, but have thermally excited electrons in the upper band. Conductivity highly temperature dependent, because basically these electrons are thermally excited, and therefore conductivity depends on the number of electrons, and it becomes highly temperature dependent. Now, the question, what about in 2D or 3D? Is the picture the same? Essentially the same, but with a subtle difference. Let us consider a 2D case, and that is sufficient to explain what happens in a dimension higher than 1D. So, in 2D, suppose I have this square lattice, so that this is the Brillouin zone. Brillouin zone would extend, this is 0, let us say this is k equals 0. So, Brillouin zone will extend from minus pi by a to pi by a in the x direction, and minus pi by a to plus pi by a in the y direction. This is the Brillouin zone, first Brillouin zone, and the block wave function psi k, where k is now 2 dimensional, is going to be e raised to I k x x e raised to I k y y times this function u k r, which is periodic. Now, the periodic boundary conditions are going to be applied over the x and y directions, and they are going to lead to k x equals 2 pi over a n over n, and k y equals 2 pi over a n over n. I may as well write this as n x and n y, where both n x and n y go as 0, plus minus 1, plus minus 2, and so on. So, the picture is really what we are doing is going into the 2 dimensions. So, I just include one more dimension, and the boundary conditions and everything, all those things remain essentially the same. Now, the number of states in a band are going to be counted by counting states in both x and y, exactly like we did for free electrons. So, now if I were to make this picture of k x and k y, there is one state in each 2 pi by L. And so on. So, there is one k x or k y state in each 2 pi by L equals delta k x or delta k y, and therefore, in the area 2 pi by L square, there is one state. The total number of states in a zone is going to be equal to 2 pi by a whole square, the area of the zone, divided by 2 pi over L square, which is L square over a square. So, the total number of states is equal to n square, and that is perfectly fine, because now in this entire Brillouin zone I will have this whole thing filled with n square states, and this n square is the number of unit cells in the area L square, because in the real space I have this crystal of size L over which I am applying the boundary condition, and I am taking each cell size to be of A. So, number of unit cells is equal to L square over A square, which is N square, and that is precisely equal to the number of states in the zone. Now, when I apply the periodic boundary conditions and take this Kx, Ky to be equal to 2 pi over A, Nx over N or 2 pi over A, Ny over N, what it is giving me is there are N square independent K values. So, this will be the number of states in the Brillouin zone or in the band. So, this implies N square is the number of states in a two-dimensional Brillouin zone, and therefore, each band which occupies all these Kx and Ky states carries N square states, and this implies each band can accommodate 2 N square electrons. So, now whatever we discuss in terms of 1D model, if I have N square unit cells in the sample and each unit cell carries one atom and each atom gives 2 electrons, then the band will be fully occupied. So, this means that if each atom means each unit cell which carries one atom contributes 2 free electrons, the band will be fully filled. Normally, yes, but in general there could be subtleties, and that is what I want to discuss now, and that is precisely what makes magnesium a metal. So, let us understand that. So, let us make this Brillouin zone which is fully filled because there are 2 N square electrons. This is fully filled. So, in the band picture, let me make it like this. In the band picture, if I have this band, I would expect that this is fully filled. In 1D, this is precisely what happened. But let us look at it slightly carefully. There is a gap at the zone boundary right here, and the next band has this band gap out here. Now, in 2D, if I start going, let us say from this point that I have made up or down along K perpendicular to this G by 2. Electrons at these levels, other levels, are going to have higher kinetic energy. If they have higher kinetic energy, it may so happen that at a certain point, let us say this point onwards, right. So, let me show this point by green, let us say this point onwards, and same thing would happen on the other side, this point onwards because of the symmetry. So, all these points have kinetic energy such that the total energy of the electrons with these k's becomes higher than the energy at the top of the band plus the gap. So, if I keep increasing the kinetic energy of the electrons in the first band, the total energy may become higher than the lowest of the next band. In that case, what would happen? All these green electrons or electrons in this green area would go to the next band. This is a subtle point, because the gaps arise at g by 2. So, they arise at g by 2. If I go away from that point in 2D, I can do that. The kinetic energy of the electrons goes up. So, what I have shown here is 1D picture, which I am again writing making marks with green. If I go perpendicular to this, the energy goes up. So, in the perpendicular direction, the energy goes up, and as the energy goes up, it may go higher than the lowest of this orange band, and therefore, all these upper electrons will start coming to the bottom of this band. As a result, neither the lower band nor the upper band would be fully filled. What would happen is that in this case, some of these electrons, the ones shown by red, will go to the higher band here, and this is because as you go perpendicular to this plane, the energy of the electrons goes higher. If I make another picture, this is the first band, these are the energies up to the top, and the second band has an overlap with it. This is the second band in some other direction. So, if it has an overlap, what will happen is half of these electrons here would move out and come here. The result being that I am going to have this band which is partially empty and the outer band which is partially filled. And these systems will conduct. These are known as semi metals. These are not metals in the conventional sense, in that the bands are not well separated, they have overlap, and therefore, some electrons from one band, the lower band, start moving into the upper band, and both are therefore partially filled bands, and they start conducting. The best example for this is the magnesium, which has 2 electrons in the last shell, and those could be free and move. In one dimensional cases, they will fill the entire band and the material would be non-conducting or insulating, but in 2D and 3D it conducts because of the overlap of the bands. So, same argument applies to 3D. So, I have illustrated with the example of 2D that bands may overlap if you go to dimensions higher than 1D, and materials may become conducting. So, to conclude, we have given band picture of metals, insulators and semiconductors, and we have also discussed how overlap of two bands gives materials called semi metals. Thank you.